Good afternoon, folks. We're going to get started on lecture 9. My goodness, we're on lecture 9 already. Just 4 more meetings until the semester's over. That's pretty wild. So here's what we have coming up. The first draft of your space mission assignments is going to be due on the 21st. That's this Friday. So I'm going to create a submission space for that. Make sure that you get them in as soon as possible so that I can give you feedback on them. If you wait a week or two and then you submit it, I can't promise I'll have time to get to everything, right? So please make sure that you have your first drafts submitted, and that way I can give you feedback as expeditiously as possible. It does not have to be with the voiceover. It should. So when you submit your first draft, thank you for the question, Christopher, so I can clarify. When you submit your first draft, I want you to have the main ideas about what you're going to be saying in the notes section of each slide. Does anybody here not know what I'm talking about when I say the notes section of your slide? I'm sorry, Tiffany, I couldn't hear you. The audio is very robotic sounding just now.
Yeah, I was saying that I'm a bit confused by what you mean by that.
Sure. So let me open up a PowerPoint here, and I will share my screen so you can see what I'm talking about. All right, everyone, we can all see the screen?
Yes.
Okay, so on the bottom, you see how, so this is PowerPoint. It's a lot more obvious in Google Chrome, and I can show you that. But if you look at the very bottom, next to the word comments, it says notes, and you click on that. And then here you can just type whatever notes you want to type about your slide, and you can make this section bigger so that your notes are there. And so when you actually go to present this, the audience would not be able to see your notes, right? You're going to be the only one that can see the notes that you put in there. So if you wanted to create an exact transcript of what you're going to say in advance of giving your presentation, this would be the place to do it. Now you can absolutely do that. I would be very fine seeing that. But for now, I just want to get the gist of what you're going to put and talk about on each slide. So like, one of the things that you have to discuss, one of the 5 main criteria that you need to talk about in your presentation is, what is one of the major instruments being used for that particular space mission. So you wouldn't just on a slide in the notes write instruments, right? I want to get a little bit more information from you so I can see, well, what exactly are you going to talk about? Are we going to talk about the mass spectrometer? And then maybe you want to say like, what a mass spectrometer does, what it does, how it's being used, what are some of the findings that have come from this instrumentation. All right, so that's kind of what it is that I'm looking for. And that way, if I feel that you should, you might need to add some more information, I'll be able to give you that feedback. Okay, so that's the note section on PowerPoint. If you don't plan on using PowerPoint, if you plan instead on using Google Slides, the note section is even more in your face. It's, let me see here. Slides.google. Right. Figured I'll just spend another moment or so showing you just in case. Okay, here you go. So let's say we go ahead, we create a new slide here. Right, Google Slides just defaults to having a speaker note section at the bottom. Put your notes here. All right. So that's that. Again, this should be submitted by 11:59 p.m. on Friday. All right, so I will make sure that after this class ends, before the evening section meets up, I will have created that submission space for you. All right, so let's get started and talk about what we're going to talk about. So at the end of the last class, lecture 8.2, we were talking a bit about, what are some of the objects that you'd find in the solar system. We were specifically focusing on asteroids and comets. And again, just looking at, yes, Chris, if you have to go for work, that's fine. So we were just looking at some of the things that we find in our solar system. And now we're going to turn our attention to stars. And we're going to talk about the life of a star. How do stars work? Right? It's not usually how we think about stars. Right? We don't necessarily think of them as an active, undergoing active processes, right? But the fact that stars emit light means that something's going on, right? They're doing something. There has to be something happening inside of a star such that it's releasing energy. So we're going to explore that right now. Let me just share the screen here. Okay. Very good. There it is. Okay. So right now we're going to look at two things. We're going to start by looking at two things. Why does the sun shine? Where does this energy come from? And how do we differentiate between luminosity and apparent brightness? We can just call that brightness. We don't need to include the word apparent, but it's helpful in conveying what it is that we're talking about. So let's start with the life of a star, right? What powers our sun? Does anybody here know? Without looking it up, does anybody here know off the top of their heads what's causing the sun to emit radiation? Let me get a show of hands if you're alive and have a pulse.
I have no idea.
Okay. How about the other 13 of you? Thank you, Tiffany. Thank you for turning your mic on and answering. I want to make sure everybody's with us right now.
Is it gas like helium and nitrogen and all that kind of stuff?
So you're suggesting maybe gas is what powers the sun?
Yes.
Right,
and
the sun. Okay. All right. It's not gas, but I like where your head's at. Alex, are you thinking like, because we use gas for cars?
Well, doesn't the sun have a core? Well, actually, wait, I'm getting confused with something else.
It's okay. Think through it, right? Think through what your current understanding is, and then we'll put, we'll put little holes in it until we figure out what's correct and what's incorrect. Also, I just want to clarify, there's a difference, like what we put in our cars is not a gas, it's gasoline, which we've conveniently shortened to gas, but it's not a gaseous matter, or gasoline is a liquid. Right, so I just want to put that out there for anybody that might have been confused. Is the sun on fire, right? Is fire what powers our sun? Well, at some point in history, astronomers asked that question, and they ran a calculation and said, well, based on the amount of chemical energy stored in our sun, or given the sun's size, given the sun's mass, we can get an idea of how much chemical energy it's holding onto. And then the luminosity is the power output, right? How quickly is the sun using that energy? And based on that calculation, the sun would only really be around for about 10,000 years. And that doesn't make sense, because we know the sun has been around much longer than that. Right? We know that the sun has been around for about 4.6 billion years or so. Okay, so it's not on fire. Is the sun contracting like a balloon that lets out gas? Like, is the sun shrinking and this is just like its energy sort of escaping, right, due to its own gravitational energy?
Well, it's
No.
nuclear fission, isn't it?
It's not nuclear fission, but it is nuclear in nature. And so this comes back to work from Albert Einstein. This is like, you can apply E equals mc squared to this. Based on the mass of the sun, it has a certain amount of nuclear energy, and given the power output, aka the luminosity of the sun, it is predicted that the sun is almost halfway through its life. It's almost halfway through its lifespan. But there are two nuclear processes that we should be familiar with. One of them is fission. What's the other one called? Nuclear fission and temperature is not a process, Alex. Right? We have nuclear fission, and then there's also nuclear blank. I'm gonna wait because I know that everybody here has heard of it. And I don't need to give a hour-and-a-half presentation to people that aren't listening. Thank you, Sani. Thank you. Nuclear fusion. All right. So these are the two processes. So fission is when an atom is split up into smaller pieces, right? Fission rhymes with division, right? And that's exactly what happens during that nuclear process. It splits up into smaller atomic particles. Fusion, however, is when the nucleus of multiple atoms come together to create something that has an even larger nucleus to it. And nuclear fusion is the process by which the sun releases energy. All right, this process has a name, and I'm going to break it down in the next 4 slides. The name is the proton-proton chain reaction. Essentially, we take 4 protons, and these protons fuse together, and through a series of steps become one helium-4 atom. But here's sort of where it gets a little confusing for people. All right, which is where the energy comes in. Let's say that each hydrogen atom has a mass of 1 mass unit. I'm just making it up. 1 mass unit. All right, so each hydrogen atom, of which there are 4, has a mass of 1 mass unit. How much mass are we starting with? Thank you, Jasmine. We're starting with 4 mass units, okay? When we put them all together and we've created our 1 helium atom, what is the mass of that helium atom? All right, let's lightning answer. Don't look anything up because I'm making up numbers anyway. All right, 4 hydrogen atoms, each has a mass of 1 mass unit. We fuse them all together. We now have a helium atom. What is its mass? What do we think? Well, Jasmine, I'm not sure how you got 16. All right. In our slide here, again, and Chris, that's the correct answer. The answer is 4, or at least that's what that's what I wanted you to say. So like, if each of these has a mass of 1, we would think this has a mass of 4, right? Except it doesn't. Right? The mass of the helium is less than 4. How does that make any sense? Well, first of all, let's think about another aspect of this. Protons, right? Or in other words, a hydrogen nucleus is a single proton. Protons are positively charged particles, right? If we try to take 2 things that are positively charged and bring them together, what do they want to do? Yeah, they want to move away from each other. They want to repel. Thank you, Barrier. They want to repel, but somehow we fuse them together and we actually get them to stick together. We get them to not repel, right? It's almost like they're glued together, right? Well, this glue, so to speak, is coming from some of the mass of these particles, right? So when we fuse them together, some of the mass gets converted into energy. And going back to Einstein's famous equation, E equals mc squared, this equation is basically saying that there is some form of equivalence between mass and energy, right? Mass is energy, energy is mass. And so when these 4 hydrogen nuclei fuse together, some of that mass gets converted to energy. And that's why the mass here of the helium is less than 4. So some of the total mass got converted to energy. Some of that energy is being used to hold the nucleus together, and the rest of that energy is released. All right, and so this process releases energy. All right, so it looks like this, okay? I'm gonna blow this up into a couple more slides so we can see it a little bit bigger. All right, but this is called the proton-proton chain reaction, and through this process, we're fusing hydrogen into helium. So in step 1, right, we start out with two protons that fuse together. And as they fuse, the products of this reaction are a neutrino, a positron, and this deuterium nucleus. Right, so some of the energy is being there's some energy being released here, some small particles, and then one of the protons essentially becomes a neutron. This happens twice. Right, so there are 4 protons initially, and they fuse together. Right. Then in step 2, the deuterium nucleus from step 1 fuses with another proton. Right. In this process, there are 2 byproducts: gamma radiation, right? That's energy being released in the form of electromagnetic radiation, and a helium-3 nucleus. This is no longer hydrogen, right? Because it has 2 protons in the nucleus. Hydrogen only has 1 proton in the nucleus. So that makes this helium. This is helium-3 because there are 3 particles. Right? And that process, this step happens twice. Then the 2 helium-3 nuclei fuse together. 2 of the protons get ejected, and what's left over is a helium-4 nucleus, a stable helium nucleus. Right? We see it has 2 protons and 2 neutrons. Right, so in this process, again, let's just look at the overall process, right? The overall reaction. We have 4 protons going in, gamma radiation comes out, neutrinos come out, positrons come out, and a helium-4 nucleus comes out. Right, so 4 protons go in, helium and energy come out of the reaction. Right, so again, here's what's going in, here's what's coming out. And the end result is that the total mass of what we're left with is less than the total mass of what we started with, because energy is released, and that's this gamma radiation. Right, the gamma radiation is why the total mass is 0.7% lower. It doesn't sound like all that much, but if you look at the amount of nuclear fusion that's going on in the sun, in its interior, where it's high pressure and it's very hot, that small percentage decrease in mass is enough to make the sun shine as brightly as it does. Okay. Right, so based on E equals mc squared, we can basically run the calculation. Given the mass of the sun, by the time all of that mass is converted to energy, you know, our sun should live about 10 billion years. Right? Are there any questions so far? anything I've said to this point that you're confused by?
No, sorry.
Okay, thank you, Tiffany. All right, thank you, Alex. Okay, so the reason that the sun is able to undergo this process of nuclear fusion is that it is stable, right? And when we say it's stable, we mean it is happy doing what it's doing, right? It wants to sort of keep the status quo of everything that's going on within the sun. You might equate or relate the word stable to balanced, right? Something that is stable is in a good balance. But a balance of what? Well, in the case of a star, there are two things that are that it is balancing, right? One is its size, all right, and there's like an equilibrium between. Well, I'll get to it in a moment. But then there's also this equilibrium or this stability in terms of its energy output, right? Which is basically saying that the energy that it's creating is equal to the energy that it's using. Right, so the balance that I was just sort of struggling to articulate relating to its size has to do with gravity, right? So our sun has a lot of mass, and we know that things that are very massive have very strong gravitational fields, and the sun is affected by its own gravitational field. It's constantly, trying to get the sun to contract. However, as energy is, as nuclear fusion is occurring in the core, there is an outward pressure coming from gas in the core of the sun. All right, so that's one kind of balance that we'll explore in a moment, and the other is that energy balance, right? And this is tying the rate of energy production to the rate of energy usage. If there were to be some kind of imbalance, then the sun's luminosity would change, right? If the sun was using or was outputting more energy than it's actually creating, right, then our sun would be getting dimmer, right? It wouldn't be able to sustain itself, right? Because it's using more energy that it can actually provide. It's like hooking a really powerful light bulb up to a 1.5 volt battery, a AA battery, right? That's not going to power the lights on the Empire State Building. Right, so there's a balance between the energy that's supplied to the star and the energy that it's radiating. If the energy that it was being provided was larger than the energy that it was emitting, then the sun's brightness would increase, right? The luminosity of the star would raise in order to use that extra radiation, use that extra energy. Okay. So here's a little diagram for you for number one, right? Just to help you kind of wrap your head around what we were talking about when we were discussing gravitational equilibrium. Right, so there is gravity pulling the sun in on itself. And then there's this outward pressure coming from the core of the star, right? That is basically saying, no, don't contract any further. This is the right size that we need to stay at. And this is actually kind of like it's like a negative, there's like a negative feedback loop that goes on here. Right, basically, if either one of these were to increase, if gravity were to get stronger or the pressure were to get bigger, the star would correct itself, right? It's like there are built-in feedback mechanisms to keep the star stable. And I will elaborate on that. in a very, in an elementary chemistry class, you might learn about the ideal gas law. That PV equals nRT. Okay, Chris, no problem. Thank you for letting me know. And so this is the ideal gas law. Does anybody recognize this? Maybe from a high school chemistry course? PV equals nRT.
I've never seen that.
Never? Okay.
At least I don't remember.
So the P in this equation stands for pressure. V stands for volume. T stands for temperature. R is a constant. And N is tied to the quantity of atoms. Quantity of atoms. Okay, getting a little cramped there. Okay, so what's going on? Well, the further you get to the core, right, the greater the pressure gets, right? And based on this equation, if pressure increases, right, if the pressure on something increases, then the temperature goes up, right? And that kind of makes sense, right? Like if you wanted to, like, if you squeeze something and you tried to compact it really small, that all that pressure would basically get the object to become hotter, right? It's like a lab-grown diamond, right? It's very, very hot due to all that pressure. But when things get hot, they also expand in volume, right? So think about this. There's gravity from the sun trying to get the star to contract. As that contraction happens, right, as the pressure on the core increases, the inward pressure from gravity, it causes the temperature of the core to rise. But as the temperature of the core rises, it causes it to expand. And when things expand, they start to cool down, right? So gravity tries to contract the star, the core gets hot, causes the star to expand, right? And so the outward pressure starts to win the battle. And then once it gets to, once the core expands enough that it can no longer really continue to push outward, gravity starts to take hold again. And it's like this constant like flux or battle, I should say, between gravity and pressure over a star's size. Right, so if the star, again, the feedback mechanism is that if the star starts to contract under its own gravity, the outward gas pressure gets larger and that corrects the shrinkage. If the star grows too much, the core cools down, allowing, causing that outward pressure to cease and the gravitational pull to start to take over again. All right, so let's just summarize a little bit about all the stuff I was just saying. All right, so what have we learned? Well, we know that the sun shines because of a nuclear process, specifically nuclear fusion. This is the proton-proton chain reaction, right? In which 4 protons fuse together, and the product of that reaction is a helium-4 nucleus, as well as some small particles and radiation, and that's our outward energy. Right. This fusion allows the star to maintain equilibrium. Right. Now, some of you might be wondering, well, that's really cool that the sun's core, has nuclear fusion going on, and that's why the sun glows. But why doesn't the Earth do that? Why doesn't the Earth emit its own light? Or why doesn't Jupiter emit its own light? Or why doesn't Mars or Venus or Saturn emit its own light? Well, because the sun is so massive. Remember, the sun's mass is like just about 98% of all of the mass in our solar system. That at the core of the sun, the temperatures there and the pressure are so high that it actually allows for the fusion of nuclei, right? And that is what then causes the star to glow. There's something on the tip of my tongue that I wanted to add. So there's a common misconception. Anybody who's watched The Lion King growing up might be under this misconception. What are stars made of? What are stars made of? Don't research it right now. Say what you've been told your whole lives. What are stars made of?
Gases.
That's what everyone says. Stars are not actually gas. Stars are not actually a gas. On Earth, there are 3 phases of matter that we are most familiar with: solids, liquids, and gases. But there are many more phases of matter than those 3. The most abundant phase of matter in the universe, the most abundant phase of matter is plasma. Plasma is it's like a gas that gets so hot that all of the particles become charged, electrically charged. It's like a giant soup of protons and electrons, rather than stable neutral atoms. So the sun is made up of plasma. Okay, so we're almost, we're gonna dig into my next set of slides to wrap up today's lecture. So we still have a couple to go. Just bear with me for a bit. As we start to explore, ultimately where we're going to go with this is we're going to look at the evolution of stars, right? What does the life of a star look like? One of the things that is important for us to reconcile is the difference between luminosity and brightness. And I feel like for people who are just introduced to those 2 terms, they might seem equatable to each other, but they're not. They are very different things. Luminosity is power output, right? It is the total amount of energy that is being released by something. Whereas brightness, on the other hand, is the amount of energy that you are receiving from something, right? And so hopefully in that wording that might make sense why there's a difference there, why there's a distinction. So like, for example, I have my flashlight here on my phone. We can all see this light, right? It looks pretty bright. Now, as I move my phone from my computer screen to back here, have I changed how much power this light bulb is emitting? Yeah. No, I haven't changed anything about it, right? It's still connected to the same battery, it's the same bulb, it's releasing the same amount of energy that it was when it was right here. But when it's farther away, it appears less bright, right? It's not as blinding back here as when it's up here. Okay, so that's one of the ways that we need to be thinking about luminosity versus brightness. Okay, hold on one second. Sorry about that. Got a repairman in the apartment right now to fix something. All right, so brightness is going to depend on how far you are from the source. The luminosity, the power output, doesn't depend on how far you are. That's just an intrinsic property of the bulb. Right, so like we can see here how in this image we have some kind of star. I'll take them. Thank you. Sorry, everybody. Got to hold on to the dog for a moment. So we can see in the slide how there's our star and that sort of growing, almost like a pyramid shape, right? With those three different sheets of paper. One has 1 box, the other has 4, the last one has 9 boxes on it. We can see how as we get farther and farther from the star, the surface area that energy is spread out over is increasing. Right, so by the time you go from 1 AU to 3 AU away, the energy is now being spread out over 9 times as much area, which means each individual box is getting less radiation. Right? It's receiving less energy. If we were 4 times further away, then we'd see 16 little boxes, right? And the amount of energy or the brightness that we would observe would be 16 times weaker than if we were at only 1 AU away. Right, so brightness depends on distance and luminosity. The luminosity of a star depends on its temperature. Right, those two are tied together. Right, more specifically, the surface temperature, because as we talk about temperatures of stars, the internal temperature and the surface temperature are 2 different things. All right. When we talk about luminosity, again, we're measuring that energy in watts because luminosity is a form of power. Power is measured in watts. So when you talk about like a 60-watt light bulb, right, you're talking about its luminosity, right? And I could take a light bulb and move it from in front of my camera to all the way back there against the wall. And while the brightness of that bulb might change, the power output will not. Okay. So here's a thought question for you. We have a star, Alpha Centauri, that is the nearest neighboring star to our own star, the sun. This is the next closest star to us. If it were 3 times farther away, how would its brightness change? Well, I'm going to go back to this slide here. Right? If it were 3 times farther away, so we're basically bringing Alpha Centauri from here and then placing it here. So it's 3 times farther away. How's that going to change how bright it appears? Well, when the distance triples, right, the energy is then spread out over 9 times as much area, which means we're only going to get about 1/9 of the original brightness. Did I lose anybody on that one? Okay, let me quickly open up my next set of slides to talk about. Give me 1 second. Okay, so when we are talking about brightness and luminosity, right, we said that brightness depends on what the luminosity of a star is, but also depends on how far away it is. All right. So what that means is that if we were able to figure out how far away a star is, right? If we were somehow able to measure the distance to a star and also record what its brightness is from the perspective of an Earth observer, right? So well, again, let me just say that in a little bit more concise way. From Earth, we can measure the brightness of the star and also measure how far away it is from Earth. Then we should be able to work backwards and say, well, based on the brightness we're getting from this distance away, this is what the power output of that star should be, right? Right, then we can start to determine the luminous intensity of distant stars that we can't get to so easily, right? In measuring these large distances, right, we use a unit of measurement called the parsec. Anybody here a Star Wars fan? Ed, big Star Wars fan. So maybe you remember in the very first Star Wars film, A New Hope, when Han Solo is basically talking up the Millennium Falcon to Luke Skywalker, he says, this ship made the Kessel Run in less than 12 parsecs, right? So maybe you've heard of it. Maybe you've heard of the context of parse. Yeah, there it is. Right. I wasn't even reading the chat. Okay, good. So you know the quote, which is kind of it took me a while to wrap my head around that movie quote, because to say that, you know, you did the, now we're getting into Star Wars talk for a second. To say that you did the Kessel Run in less than 12 parsecs, that's like saying I did a mile run in less than 1 mile. And that's like, wait, what a sec? What? How does that make any sense? Okay, you know, I'm not going to finish that thought. We could talk about that after, because now I'm starting to nerd out a little bit too much. A parsec is equivalent to about 3.26 light years, which means a parsec is very big, right? Now, to measure the distance to objects, we're looking for parallax. Remember, that was the thing that the ancient Greeks were not able to detect way back when they were deciding whether or not the solar system was heliocentric or geocentric. All right, but to do that, it requires you to, one, know what is the distance from the Earth to the sun, and two, what is this angular size? Or what is how much does the distant star appear to move across the background of further stars, right? If we can figure out what this angle is here, and we know what the distance is between the Earth and the sun here, then a simple tangent function, right, a trigonometric function, would be able to tell us what the distance is from the sun to that star. Right, so stellar parallax is essential here. Right now, once we are able to figure out a star's luminosity, again, so now we're saying, here's the brightness of the star, here's how far away it is from us, therefore this must be the luminosity of the star. Once we can get to that point and figure out what a star's luminosity is, and then we can start to talk about its temperature, right? And this brings us into spectral types. Right? There are 7 spectral types for stars, and they correspond to different letters. The letters are indicated here: O, B, A, F, G, K, M. There are a lot of mnemonics used to help memorize that. There's like, oh boy, a fine. Well, when I was younger, it was, oh boy, a fine gal or guy, kiss me. But now I think that it's probably better to avoid using guy and gal and probably say, oh boy, a feisty giraffe, kill me, or something like that. Whatever floats your boat. Right? And these spectral types are based on temperature ranges and also looking at spectral lines, right? That's why we're reintroducing the word spectral here. So when we look at distant stars, we can say, let's look at this really, really hot star. And we see that it's, it almost looks like a continuous spectrum. Right, there are some lines corresponding to hydrogen that are very weak. Right, they're not particularly dark. We got some purple wavelengths missing, some blues, some reds, and then we get to the B spectral type. Right, so an example would be the star Rigel, whose temperature range goes from 10,000 Kelvin up to 33,000 Kelvin. Again, O-type stars are 33,000 Kelvin and hotter. And back to spectral type B, what we start to see is that the hydrogen spectral lines start to come a little bit more into play. They get a little bit darker here. As we get down to spectral type A, you can see that they get significantly darker. All right, so this would be like the star Sirius. Right, the temperature range is a little bit more limited here. Okay, every one of these different kinds of stars, or rather every one of these different kinds of spectral types has a brightest wavelength, right? A part of the spectrum that is emitted with the greatest intensity. And so, for example, for Sirius, it emits violet light more than any other colors, whereas Polaris, the North Star, emits mostly blue light, and that's why it appears blue in the night sky. Polaris, we can see those hydrogen lines start to weaken a bit, and we start to see some of the spectral lines from other atoms, like calcium is in here, there's sodium, right? As we get into spectral type G, this is where our sun fits in, and this is the category that our sun falls into, as does Alpha Centauri A, our nearest stellar neighbor. Right? Again, we're looking at a temperature range that's less than what came before it. The surface temperature of our sun is about 5,800 Kelvin, so it's right near the upper end of this range, and it mostly emits yellow light. And that again is why our sun appears to be yellow. Then there's Arcturus. All right, even cooler in terms of its surface temperature. Again, we're talking about surface temperature here. Here we're starting to see a lot more absorption lines in this absorption spectra. We're not really getting the hydrogen lines anymore. Now we're starting to get lines from metals and other larger molecules that are in there. And by the time you get down to spectral type M, right, these are very low temperature stars by comparison. We're getting more molecular lines than anything else. Right, so these spectral types go from hottest to coolest, right? So, oh boy, a feisty giraffe. Oh boy, a feisty giraffe kicked me. How about that? There are any Harry Potter fans in the room? All of the members of Sirius Black's family were named after stars. I don't know if anybody knew that.
What? No. No, this is
Uh-huh.
mine right now.
Uh-huh. There's Regulus Black, Sirius Black. Bellatrix is a family member. You can look it all up. It's all on the internet. You can find that floating around somewhere. Right. And let's see.
But it's crazy because they were all iconic too.
They were all quite iconic. Okay, so now I'm just going to skip ahead a little bit. All right, so this is a diagram, a graph showing you on the top axis temperature, on the bottom axis spectral type. You notice how the temperature axis and the spectral type axis are parallel, right? Because they're measuring similar things, right? So again, we have the O spectral type is the hottest, M spectral type is the coolest, and then we have the strength of lines from different atoms and molecules, right? So one other thing I want to point out is that within these 7 spectral types, there are subdivisions of those spectral types, right? So we then introduce numbers that go from 0 to 9. So like starting here on the bottom, it starts on the graph with 05, but then you have 06, 07, 08, 09, B0, B1, B2, B3, B4, B5, B6, B7, B8, B9, A0. Right, and that way we can break it up a little bit and be even more specific about which spectral type we're talking about. All right, so for a star like our sun, right, our sun is, oh God, is it G2 or G5? I don't know, it's not really clicking in my head right now. But our sun would have sort of weak hydrogen lines. We would have some strong iron and calcium lines. Calcium 2, we get some iron 1 and iron 2, a little bit of calcium 1, but we wouldn't really see any spectral lines related to helium or silicon or magnesium. Right? Those are more prevalent in the hotter stars. I also want to point out another thing that is odd for people when they look at these kinds of graphs. It's that temperature decreases as you go to the right. Typically, when we look at an x-axis, a horizontal axis, we see that as we go to the right, from left to right, the numbers increase. But here, the numbers actually decrease. Sorry, temperature is getting cooler as we go from left to right. Okay. So here, we're looking at a spectral type A star. These stars are fairly hot, right? And we have here, actually, what's on my next slide? All right, so anyway, these stars are fairly hot. You can see based on these curves. So this is actually a black body curve, right? Coming back to black body radiation, which we talked about a couple of weeks ago, you had your lab on it. We can see in this curve that it's not a perfect black body. It's an approximate black body, but also there are dips related to specific atoms in the atmospheres of these stars, right? And so when we see these lines, right, that's one way to figure out, look, we're seeing a lot of these hydrogens and not really any calciums or any titanium oxides. This must be a spectral type A star. And that's what astronomers are able to do, is look at these graphs of wavelength versus frequency or intensity, I should say, not frequency, but intensity, and be able to determine what is the temperature of a distant star. All right, so this is a spectral O star. This is the hottest. You see that again, we've got those hydrogen lines that are very strong. And we got those, and got some helium lines in here also. Right. As the star gets cooler, remember what happens in a black body curve? The cooler the star is, the smaller the curve gets, but also the more it shifts over into longer wavelengths. Right. So as we go from this O type to what, whether this is a B or an A, right? We see how the peak of the curve goes from being over here, right around just a little bit above 4,000, to over here, which is closer to like 4,600 angstroms is the unit of wavelength that we're using here, right? And we get different elements that are starting to show up. We've got some magnesium dipping in. And if we go to the next coolest, right, we can see again the peak wavelength has shifted over. It's somewhere in here, right, in the 5,000 range. Although it looks like it's dipped out because of the presence of the magnesium in the atmosphere. Based on the rest of the shape, this somewhere around here is where the peak should be. Right, and we're starting to see that calcium on the right. We've got some sodium all up in there. Right, as we get even cooler, you see how the peak shifts over to the right even more. Right, those magnesium lines are really strong. Right, you can see just how much they're dipping down there. The sodium lines are getting stronger as well. And down here, right, by the time we get to spectral type M, look how much the peak wavelength shifts over. All right, it's like around here somewhere, right, in nearly the 7,000s. So it also starts to look much choppier, right? And that's because all of these molecules that are able to form because it's a little bit cooler, right? They absorbs a lot more of that radiation. Okay. That is where I'm going to stop for right now. And I'm going to end the recording. All right, if anybody has any questions that they'd like to ask, now is the time to do so. If there's anything that you want to clarify for the space mission assignment, I encourage you to ask those questions now so that others can listen in. And with that, have a great day.